Electricity. We use it every day of our lives. It starts our cars, lights our homes, cooks our food, runs our television sets. The list of things it does for us is very long. Right now, for example, you wouldn't be seeing me or hearing me if we didn't have electricity. Yet, even though electricity plays such an important part in our day-to-day lives, most of us don't understand it. The work you'll be doing in this program will give you a basic understanding of electricity. For example, how electricity is generated and how it behaves in electrical circuits. And once you know that, you can go on to learn such things as how to maintain and repair electrical equipment and to do it all safely. Let's look at some basic concepts of electricity. This simple circuit has a power source. This old-fashioned hand-crank generator. Connected to the generator is copper wire that leads to a switch. This switch can connect either this light or this bell to the generator. Let's start with the light. Electricity is generated by turning the crank. As long as the crank is turning, the light bulb stays on. When it stops turning, the light goes off. We've used electricity to do some useful work. That is, to light the bulb. Now, moving the switch to connect the bell, we can use the electricity to do a different type of useful work, ringing the bell. But what has really happened? Let's take a close look at a length of copper wire, like the one in the circuit we just saw. As you can see, the wire is actually made up of two materials. The inner material is a metal, in this case copper. We call the copper a conductor. A conductor is a material that allows electricity to flow easily through it. Around the conductor is an insulator, in this case a plastic material. An insulator is a material that doesn't allow electricity to flow easily through it. So when the generator is cranked, electricity flows through the conductor, not through the insulator. So far, we've talked about electricity flowing, but we haven't even begun to explain what electricity is. Well, the dictionary defines electricity as a flow of electrons. But what's an electron? An electron is a tiny particle, that is, a bit of matter smaller than an atom. In fact, an electron is a part of an atom. And atoms, of course, are what everything in the world is made of. When we can get electrons to flow away from their atoms in a single direction, we have electricity. Let's take a look at how electrons flow. This isn't a direct look, unfortunately, because no one can see electricity. What we'll do is represent the flow of electrons through a wire. People have come up with a lot of ways to represent this flow, but the one I like best is this. In this demonstration, the conductor, the wire, is represented by this tube. Each ping-pong ball represents an electron. As you can see, the ping-pong balls aren't moving through the tube because nothing is causing them to move. But all we have to do is apply a force to the ping-pong ball on the end, and the balls start to move. Let's do that again. You'll notice that the first ball doesn't go all the way through the tube. It just pushes the second one, which pushes the third one, and so on. When force is applied to the electrons in a conductor, they move in about the same way. And that movement is called electricity. Now remember, we said the tube represents a conductor, and that a conductor allows electrons to flow easily, as these ping pong balls did. And that's because there are a lot of electrons available to flow. Just like in the tube, there are a lot of ping pong balls available to flow. If we apply the same force to an insulator, electrons won't flow as freely. The reason is usually because there are fewer electrons available to move. This is a representation of a conductor and insulator. The artist has shown the material cut in half so we can visualize electron flow in each material. The electron available to flow are shown as dots. The conductor has many available electrons, so when a force is applied, the electrons flow easily. Now let's look closely at the insulator. You can see it has some electrons available to flow, but not many. So a similar force will not cause continuous electron flow. A much greater force will cause a little more flow, but electron movement still doesn't continue. This is because of the nature of the material. Silver, copper, and aluminum are examples of good conductors. And rubber, plastic, glass, and dry wood are examples of good insulators. A common use of a conductor and insulator used together is this wire. It has a copper conductor surrounded by a plastic insulator. So by turning the crank on the generator, we start electrons moving through the conductor. Turning the crank on the generator is like pushing the ping pong ball in our model. It has the effect of creating a force that pushes electrons along in a single direction. That is, the force results in electricity. Now, no one can see electricity, but the light bulb is on, so we know electricity is flowing. Of course, when we stop cranking, we stop the flow of electrons, and we don't have electricity. Let's review. We know that electricity is the flow of electrons in a single direction. And of course, we know we have to apply some kind of force to get them moving. In our example, we used an old-fashioned hand-crank generator. We also know the difference between a conductor and an insulator. A conductor has more electrons available to be moved. A good example of a good conductor is copper. An insulator has fewer electrons available to be moved. An example of a good insulator is rubber. Simple? Yes, if you don't want to know any more than that about electricity. But not if you want to learn enough about electricity to be able to maintain, repair, and troubleshoot electrical equipment. So after you've reviewed what we've talked about so far, we'll move deeper into our subject.